Okay, let's talk a bit about, let's see, pressure, flow, and resistance within the circulatory system. So the relationship among blood pressure, blood flow, and the resistance of blood, when we look at all that together, we call that a term called hemodynamics. In science, we get a lot of dynamics, thermodynamics, hydrodynamics, fluid dynamics, and when we look at the body, the flow of blood through the circulatory system is hemodynamics. And blood flow, we can call that F. So some of the terms that we need to determine and make this work is blood flow equals letter F. And it always goes from an area of higher pressure to lower pressure. So there needs to be some type of pressure gradient in our system, in our blood pressure system in our body. The pressure of the blood leaving the aorta is 120 millimeters of mercury, and by the time it returns into the right atrium, our pressure is almost zero at that point. So we have a very large pressure gradient to move blood through. So the pressure, though, pressure exerted by any fluid is called hydrostatic pressure. Just call that pressure, though. And it denotes the force generated by the contraction of the heart. In our example, it's 120 millimeters of mercury. So when we look at rates of flow, they're usually measured per unit time. So we look at it as flow rate as liters per minute or milliliters a minute. Pressure difference would be, we would note that as a delta P. And then just because you know the pressure difference between 2 points, it's not going to tell us the flow rate. So we need to know what the resistance is, which we're going to call R. It's essentially how difficult is it for the blood to flow between 2 points. So if we have a blood vessel and we have point 1 and point 2, and we have a flow that's going this way, and at P1 we have 100 millimeters of mercury, and at P2 we have 10 millimeters of mercury. Our delta P in this case equals 90 millimeters of mercury. And then since we can look at our flow rate is equal to the proportion, or the delta pressure, the change of pressure divided by R, we can calculate this we know our flow rate in this case to be 10 millimeters a minute. And at that point we can calculate our resistance from there. So 10 equals 90 divided by R equals 9 millimeters of mercury is our resistance per milliliter per minute. Those are our units. So that's an example of how flow rate, pressure, and resistance are all related to each other. So one of the things that we should think about is once the determinant of resistance is a word that we know as viscosity. You might know it from your oil in your car. The oil has a much greater viscosity than what we see in water. And this is just a function of the friction between the molecules of the fluid. The greater the friction, the greater the velocity or viscosity. And this follows something that we call Poiseuille's law. My French is a little crummy, which gives us, goes this way, equals 8 L over pi r to the 4th power. So that's our fluid viscosity. 8 pi is a constant. This is the length. And then r is the radius of the tube, or a blood vessel. So the important thing to know about this is this function right here, our radius. It's to the 4th power. So this is going to say, let's use the example of we have a radius of equals 1 and a radius equals 10. So if we were to put everything in here, look at it from this way. I'm just going to do it this way. That way we're not confused with our resistance here. We can use r equals 1. So at the bottom it will be 8 times our fluid viscosity pi 1 to the 4th, or 8L viscosity times pi times 10 to the 4th power. So we can look at it from that way. This is going to be 1 at the bottom, or on our other one, we are looking at a function of, let's see, 10 times 10 times 10 times 10, which is going to, oops, did a little math here, times 10 times 10. It's going to give us 10,000 on this side. So you can see this portion right here has a great effect on flow rate. The radius of our tube is going to be our greatest determinant on how much flow goes through our tube at this point.